Welcome to everyone. Okay. I'm very honored to introduce to you Professor Philip Wadler. He is an authority in the field of programming languages. He is a fellow of many important institutions. He is a recipient of many important awards. He is author of a huge number of highly cited papers. And it's also well known in the community of students because he contributed to the design of Haskell, Java, and XQuery, which are languages that are also taught in the degree of computer science. He's also known to the community of logicians because, and they see here, and I'm hosting him. I want also to, lastly, to remind that he will give lectures as introduction to Agda on Wednesday, tomorrow, and Thursday in the laboratory, TA, the second floor, from 12:30 until 3:30 with some break. And I really would like to thank the group of logicians and the group of computer scientists for having founded this his visit so that he can deliver this lecture. I also would like to thank the department for having founded this seminar. So thank you very much, please.
Okay, thank you. I have to do both. Okay. No? Can you hear me? Hello. This is quite a good turnout. Thank you all for showing up, especially since the weather, unlike what was promised, the weather is actually nice. So you could be outside enjoying the last of the good weather, but you're here. So I'm very grateful for that. Thank you. I dressed up for you, but it's actually rather warm, so I'm going to take off my jacket if that's allowed. Is this too informal? Okay, so somebody said, oh no, you look like you're on vacation, but too bad. It's work, but it's a great pleasure to be with you. So thank you to Maria and Gilberto for inviting me here, and for all of you for giving me a reason to be here in Padova, which is a very nice place to be. My wife and I are enjoying it very much. So thank you for living in such a lovely city as well. Right. Are there any questions? All right, I have some questions. So she began by mentioning 3 languages. How many of you actually use Haskell? Okay. Java? Ooh, about the same. XQuery. That's what I thought. Oh, you've heard of it. Okay. Is it actually taught here, XQuery? I'm amazed. Yeah, that sounds about right. So everybody's taught XQuery and nobody remembers it. Okay, that's probably for the best. Anything to do with XML. Good. And the other question I had, how many people are here because they're going to be attending this tomorrow? 1, 2, 3, 4, 5, 6, 7, 8, 9. Thank you again for giving me a reason for being here. I'm going to take the same vote at the end and see if the number changed and whether it went up or down. Okay, so I've written a textbook. It's called Programming Language Foundations in Agda. I work at the University of Edinburgh, but my wife is only allowed to be in the UK for half the year. So the other half the year, we live in her hometown of Rio de Janeiro, which is a great place to do functional programming because, as you can see, the streets are paved with lambda symbols. But what I always advise everybody else to do, if they can begin their talk with a demonstration, to do that rather than to just use slides. So you can see I've got lots of slides here, but we may go back to those later or we may not. I'm going to ignore that for now. And here it is. So this is the textbook. This is the official published version of the textbook. It only exists on the web right now. Maybe a publisher will publish it someday. But there are lots of good things about it being on the web. So one is, of course, that it's easy for you to access. One is this whole book is actually a literate computer program. So let's look at this first chapter. So the first chapter begins by introducing you to natural numbers. And it begins in very flowery style. The night sky holds more stars than I can count. Though fewer than 5,000 are visible to the naked eye, the observable universe contains about 70 sextillion stars. But the number of stars is finite, while the natural numbers are infinite. Count all the stars, and you'll have as many natural numbers left over as you started with. So this is a flowery way of making the point that the data type of natural numbers is really big, right? It's infinite. And there's something special about infinity, right? In computing, we make a big difference between finite things and infinite things, right? Finite things are really easy. You can just always deal with them with a finite state machine. But for infinite things, you need something more like a Turing machine, right? Infinity is where things get interesting. So how do you define infinite natural numbers? Well, how many people here are familiar with a little bit of type theory or a little bit of data types in functional programming? Okay, not that many of you. So here's the most important thing I'm going to say in this whole talk. If I say something you don't understand, please ask a question. Right? That will help me, and that will help the other people in the audience who also don't understand, as well as helping you. And if lots of people ask questions, I feel like I've given a good talk. If I get to the end and there have been no questions, and then my host says, are there any questions? And everybody sits there like this, then I know I've given a really bad talk. So I look forward to your questions. Are there any questions yet? Not yet. Okay. So here's the definition of the natural numbers. The data type funny n is set. SET is the way in Agda that we spell type. So this just means it's a type or set or kind of things. And there are two ways of constructing them. 0, which is a natural, and successor, which is a function that takes natural to natural. This is sometimes called Peano's definition of the natural numbers, going back to the mid-1800s. Dedekind actually got there a little bit earlier, I think. How many people are familiar with that definition? Everybody. Good. No, not everybody. Nobody in the back there is raising their hands. I'll try again. How many people are familiar with this definition? Nope, there's still people not raising their hands. Good. Would you like to ask a question? Seriously. Yes, I'm looking at you. Have you seen this definition before? Okay. So what it tells us is, would you like to ask a question? So ignore her. She's a bad example. You should ask questions. So what this is saying is that, right, this tells us 0 is a natural number. But then what this tells us is that anything that's a natural number, we can apply suc, that's short for successor. We can apply suc to it, and that gives us another natural number. So that means since 0 is a natural, suc of 0 is also a natural. Oh, wait! Suc of 0 is a natural, so I could apply suc to that and get a natural. So we've got suc of 0 is also a natural. And then because of that, we've got suc of 0, and so on. And how long do you think I could keep doing that? Right, for a long time. So this gives us, right, that dot, dot, dot there is covering more things than I could write down if I wanted to. Right, that's an infinite number of things. By the way, that's the only time it's legitimate to use dot, 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 is if you can't write out everything. Otherwise, write it out. I've read so many things written by people who would write dot, dot, dot at some point, meaning I don't want to slow you down, and I'm sure you know how to fill this in. And I'm sure the author knew how to fill it in, but I had no idea what they meant to go there. So unless it's an infinite number of things, in which case you have a really good excuse for not filling them all in, do not write ... if you can help it. So in this way, right, we've just got 3 lines here, but we have defined all of the natural numbers. All of them! Right? They're really a lot. So this is a very basic idea in mathematics. As I said, it goes back at least to the mid-1800s. But it's a really, really important idea. This notion that you can cover an infinite number of cases in a very finite space is really important. And then the next thing I wanted to show you is, oh, why didn't that work? I know why that didn't work. The textbook, you can actually download it on your computer. So here is the source of that textbook. So this, right, all typesets nicely, and it's written in Markdown, right? So this thing where it says ## turns into this thing where you get a nice header, and then the bits I write in code blocks turn into nice bits in blue, and so on. So all of this nice typesetting comes automatically from what I've written here. But this, I can edit and change and execute. So here's the most important thing you can do with the book. This is really exciting. I'm typing, well, I'll do it here. So in the Agda menu, I select load. Look what happened, right? This turned into color. And this window appeared, and that window has absolutely nothing written in it. Okay. Now, that may not seem very exciting, but this window is where all the error messages appear. So the fact that this window has nothing written in it, and that this changed color, means Agda successfully loaded the program, and there are no errors in it. Right? If I changed it by adding something that's not correct, I think that's not correct, and now if I load it, yeah, now it gives me an error message, right? No declarations allowed after top-level module. Okay, they're not necessarily always easy to read, right? It thinks the error is here with my first data declaration, but actually the error is here where I put in the word wrong, right? So the great thing is, right, this gives the students lots of immediate feedback when they've got things right. And when they've got things wrong, it gives an error message. I will warn those of you who are going to be in the class, sometimes you will understand what the error message is, but sometimes the right way to deal with the error message is to raise your hand and say, Phil, can you come over here and explain this error message, please? The error messages are not always as clear as they might be. Okay, but then, so we can see, indeed, that this changed color. So this bit is the program, and there's some color coding here. So red things are keywords, things in blue are defined names, and things in green are constructors. Constructors are very important because they're the way you build a data type. And constructors are then important because they can appear on the left-hand side in definitions. So let's skip down. Here's an interesting thing we can do with natural numbers is we can define addition. So if you were like me in grade school, you had to learn addition tables, right? You had to learn things like 4 plus 5 is 9. We've just memorized that. And there's a big table, and then there were lots of rules for adding things up and doing carries and so on that let you add things. So here, we're using a very simple representation, right? It's called unary, right? Because if you write out something like 7, I think 7 is up. No, 7 is an exercise. Right, the length of a number, you'll have as many sucks as there are in the number. So the number 1,000,000 would take really a long time to write down because it would take more than 1,000,000 characters to write it down. But that's okay. We're just trying to theoretically define things. And for theoretical definitions, it's much easier to use unary. As I said, this goes back to the mid-1800s. and the work of people like Dedekind and Piano. There's an exercise later for doing binary representations, which are much more compact. But how would we define addition, right? There are an infinite number of things, right? So we could just write out a table, but the table would be infinite number of columns and an infinite number of rows. So it would take us too long to write out. So here's a way of doing it without doing that. And again, it's just 2 lines long. So this tells us that plus is the name of what we're defining. The underbars tell us where the arguments go, so we can use infixed notation. This is a way of saying we have a function that takes 2 natural numbers and returns a natural number. And then there are 2 cases here. 0 plus n is n. So if you add 0 to something, it doesn't change. And successor m plus n is the successor of m plus n. So this is a recursive definition, and it tells us that how do we add successor of m to n? So for instance, right, we might be adding 2 to 3. So 2 is successor of 0. So that would match this equation by saying m must be the successor of 0. So then here we're saying take the successor of 0, that's 1, and add it to n. So this says to add 2 to 3, say, what we do is we add 1 to 3, and then we add 1 to that. So 1 plus 3 would be 4. 1 added to that would be 5. So 2 plus 3 is 5, as you'd expect. And I actually write that out in detail here, using all the sucks. But let's just assume, right? Agda actually has an abbreviation. It knows that when you write 2, that stands for suck 0. So here's the same thing written out more compactly. So how do we know that 2 plus 3 is equal to 5? Well, 2 plus 3 is, for the reasons we just saw, the successor of 1 plus 3, which is, for similar reasons, the successor of 0 plus 3, which must mean 0 plus 3 is 3. So it's the successor of the successor of 3, but that's just 5. So there's the computation telling you that 2 plus 3 is 5. Now notice this is a recursive definition. Right. How many people have encountered recursive definitions before? Okay, that's almost all of you, but not quite all of you. So I live in the UK. In the UK, there's this saying, Brexit means Brexit. Everybody laughs at us for it, as well they should, right? And what any mathematician will tell you is, this isn't telling you anything, right? If you say Brexit means Brexit, there's no new information there. And in fact, this is a recursive definition, but it's not well formed. It doesn't give you any information. In denotational terms, we would say Brexit is bottom, the thing that has no information, according to that equation. Maybe according to some other ways of evaluating it as well. But this definition, even though it's in terms of itself, it's well-founded. It means something. And the reason for that is we define, here we're defining 0 not recursively, and then any other number is defined in terms of a smaller number. So this defines adding 2 in terms of adding 1. Adding 1 is defined in terms of adding 0. Adding 0 is just defined. So everything is defined in terms of something smaller. If you keep going down, eventually you reach 0. That's called a well-founded definition. And then the 0 case is defined. So this is, in fact, always defined. And Agda checks this for us. Whenever we write a definition, Agda will tell us, Agda will tell us whether it's well-defined or not. So here it's perfectly happy, and that's because plus here, when we call it recursively, it's on M, but here it was on successor of M. So here it's being called on a part of what it was being called on originally. And this is why constructors are so important, because constructors are what can appear on the left-hand side of an equation, and it's a constructor that you use to get smaller. Okay? And then because this is online, right, I can just execute it. I can delete the whole thing. I can put in my own favorite equation. Let's say I want to just define m plus n to be something. So this question mark stands for what's called a whole. If I execute that, then it gets unhappy because I've told it what natural numbers are. That's the one definition I can't do this with, damn. That's okay, hold on, we'll go back. We'll go back, there we are. What I'll do is I'll just comment out the rest for the time being so it won't get unhappy. There we go. That one we can leave in. Okay, so now I do this, right? It gives me a whole. I can go into the whole and say things like, do a case analysis on M. So I type Control-C, M, return, la-la! It broke it up into equations for me. So it said, if you want to do a case analysis on M, the two cases are going to be 0 and successor of something. Let's call that M as well. That's a good naming convention. And then here, if I say guess a number to fill in, it can act, oops. Oh. It guesses, n's the only thing it could guess, right? Or it's the simplest thing it could guess. It could have guessed successor of 0. And so when you add 0 to something, it's always 2. But it makes the simplest guess, which is n. And here, right, guessing will not work well for us, right? It also guesses n. That's not what we want. But we can say, right, what constructors could I use here? It says, I don't know. You could use 0 or successor. So I can write in successor. And then again, when I get to here, okay, I want to put in a recursive call. So let's recursively call m plus n. And that says, yep, that type checks. Okay, so it gives you a lot of help in coming up with definitions. And if I did a stupid definition, right, like this definition should not be allowed, right, or this here we're defining, well, here's a definition that's correct but not allowed, right? This is true. Successor of m plus n is also equal to m plus successor of n, but now n is getting bigger. M is getting smaller, but n is getting bigger. So this will not be allowed, I think. Oh. Why is that allowed? Uh-oh. That shouldn't be allowed.
Because n got smaller.
Oh, right, this will actually work, won't it? Haha, right, this will also work. It'll take m down to 0. Okay, that's why it was allowed. But if I wrote this, if m was not getting smaller, right, now it says, nope, termination checking failed. In other words, I can't prove this terminates. And in fact, this would get into an infinite loop, just like Brexit. Actually, saying Brexit means Brexit was prophetic, wasn't it? Because it did go into an infinite loop. That's right. It can only prove things terminate by saying you're acting on a part of what you had before. Right, I'm just going to rewrite this exactly as it was, because I don't really want to change the textbook. Okay, there we go. So there we can do definitions. I'm just going to show you a wee bit of the next chapter. What we can also do is prove things. So like here's the simplest thing you would want to prove, which is that plus is associative. And again, this is checked. Let's check the proof for us. So this is a proof that for all m, n, and p, that m plus n plus p is equal to m plus n plus p, parenthesized the other way around. How many people are familiar with the term that saying that addition is associative? Right. How many people know how to prove it rigorously? Right, just the logicians among you. The rest of you are more sensible than to waste time on this. Right, but especially if you're doing computer programming, where you're finding new things all the time, you might want to define a new data type and a new operator on it and show that that operator is associative. That's actually an important thing to do. So knowing how to do a proof and how to get a computer to check the proof is a very helpful idea. So here we're doing that. And what we're going to do is, again, a case analysis. And we're going to look at m. And we're going to say, right, either m is 0 or m is the successor of some number, which we'll also call m. So our first argument is either 0 or successor, just like with the definition of plus. Then we've got two other arguments. And if it's 0, then this left-hand side, right, m gets replaced by 0, so it becomes 0 plus n plus p. But 0 plus n we know simplifies to n plus p. The right-hand side also becomes 0 plus n plus p, which also simplifies to n plus p. So as usual with this style of a chain of equations, what we do is we start reading from the top to the middle, simplifying, and from the bottom up, simplifying. If you get to the same thing, you're done. Similarly, here we've got successor. So successor of m plus n is successor of, in parentheses, n plus n. But then we're adding that to p. So again, that's the successor of something. So that becomes the successor of, and then recursively, m plus n plus p. That's reading down. Reading up, we have the successor of m plus n plus p in parentheses, which again simplifies to the successor of m plus n plus p in parentheses. Now, at this point, we simplified each of these as much as we can. Oh, but wait, by induction, that is, by the same thing we're trying to prove, but on a smaller number, right, on the previous number, we know for the previous number, by induction, that m plus n plus p parenthesized one way is m plus n plus p the other way. So we have this term and this term are equal by plus a soak of MNP. That's what we're proving. It's a recursive call. And then we want to write suck in front and still have the two things be equal. And that's true by congruence of suck. So that just says you can apply anything to two equal things and they'll still be equal. Right? Function of x and function of y. If x and y are equal, function of x and function of y are equal. That's the type of Kong, right? We can actually click on Kong and it will give us the definition, which says exactly that. For all functions from a to b, and for all x and y, which it can work out will be of type A, if x is equal to y, then f of x is equal to f of y. And I won't show you how we define that or prove it, but all of this can be defined and proved using the techniques that I've shown. So this is rather nice. This shows us that proof by induction is the same as a recursive call. That's all there is to it. And it also shows us that proving something is true for all of three different arguments, that's just a function of those three different arguments, which returns a proof of whatever this formula is, and this formula can mention the arguments. So that's called dependent typing. Or if you're used to predicate logic, right, this is just a quantifier with a formula following it that, of course, mentions the quantified variables. So proofs of universal quantification turn into functions where the type of the result depends on the value of the argument, not just the type of the argument. And that's it. So just using these tools, we can do everything you'd ever want to do. So the way the textbook works is the textbook is in two parts. The first part is just showing you enough Agda to be able to do all of logic. And so we learn things like naturals and inductions, and how to define a relation, like less than or equal, how to define equality, how to define isomorphism, how to define things like conjunction, disjunction, and implication for logic. This is and, or, and if then. How to define negation. And at this point, I finally come clean and mention we're dealing here with intuitionistic logic, which is very important. So it means you don't have the law of the excluded middle. And we go into why that's true. Quantifiers, which we've already seen. Decidability, which is so here you learn how to define less than or equal. Here you learn how to write a program that given two numbers will tell you if they're less than or equal or not, and give you a proof that the relation you defined here holds. And lists, which are sort of an important data structure, and also lets us talk about higher order functions, which are an important technique in programming. And then in part 2, we go on and give the basic theory of programming languages, which is lambda calculus, properties of typed lambda calculus, a different way of formulating typed lambda calculus. This is more compact than this one. So I do both so that people see both. This one's more compact, so I use it for the rest of the course. And then we can define lots of other constructs, many of which we've seen earlier in the book. This is about how to do type inference, which says, given something here where the types are not part of the term, how do you get something here where the types are part of the term? And then this gives variants of lots of things. So everything I've shown here is call by value, not reducing under lambda terms. And here we just show something a bit different, which is call by name, reducing under lambda terms, and not having distinct types so that everything is untyped. This was the original lambda calculus. So we show how to formalize all these things. This is as far as the book goes so far. But one nice thing about writing a book online is other people can then just go and do things. And my colleague Jeremy Seek has been writing denotational. So this is what's called operational semantics. And Jeremy Seek has been writing what's been called denotational semantics. So there's 2 more chapters explaining other properties of lambda calculus, things like confluence and denotational semantics. So those will get published soon, I hope. They're getting ready to be shown to the public. So that's the book. Let me now go back to the lecture. How long have we got? Okay. Oh, let's go back here. So Agda is part of a family of things called proof assistants. There are lots of them. The first one was LCF, Logic of Computable Functions, and it had a meta language for writing things down called ML. ML is the ancestor of every single typed functional programming language. So it's the ancestor of Haskell. What's your other favorite typed functional programming language? Nobody has one. Yes? OCaml. It's the ancestor of OCaml, which in fact has the ML in its name. It's the ancestor of all the other ones. I actually took my post at Edinburgh because they said, would you like Robin Milner's old chair? And I said, wow, that would be very nice. So I went there, and when I got there, they said, here's your office, there's his chair. There was a system that followed on from that called Coq, designed by Gérard Huet and Thierry Coquand. And Coq has been used for a lot of things. So it's become famous for things like a proof of the four-color theorem, completely verified by computer, right, which was important because the original proof of the four-color theorem had 20,000 cases to it. And the only way they could do that was by writing a Fortran program that would check all 20,000 cases. So it's quite good that you can actually, instead of writing it in Fortran and doing a proof by hand that should be all right, doing it in Coq and absolutely proving that checking all these cases is correct. Another thing that has been done in, by the way, the proof of the four-color theorem was done by Haken and Apple, and it just so happened that they both had children that went into computing and were colleagues of mine when I was an undergraduate. And Andrew Appel, the son of the guy who did the first proof of the four-color theorem, not the proof in Coq, but the very first proof with the large Fortran program. He now spends most of his time working in Coq doing other things. So Coq's done lots of things, including a complete C compiler that has then been proved to match its specification. New ideas for nice ways of doing pattern matching were developed in a system called Epigram, which was done by my colleagues Connor McBride and James McKenna. I work with them all the time. They're both in Scotland. But they never finished implementing Epigram because all the good ideas in Epigram were then adopted into Agda, which is what I will be teaching over the next couple of days. And Ulf Norell and Andreas Abel and many others developed Agda. People wonder, by the way, why is it called Agda? Agda is a Swedish name for a female hen. So it's the counterpart to Coq. And then you'll see the name of the book is Programming Language Foundations in Agda. So one thing I need to explain here, one thing I should stop to explain, is that the book, do I want to do this? Right. How many people have heard of the idea of Curry-Howard isomorphism or propositions as types? Sorry? Curry-Howard correspondence, yes. So I'll just quickly review for the half of the audience who's here. If you look at rules in logic for things like conjunction, the rules are things like, how do I know A and B is true? Well, it's true if I can prove A and I can prove B. What do I know if A and B is true? Well, there are two things I know, right? One thing, if I proved A and B, I can conclude A. And of course, the other thing, if I've proved A and B, is I can conclude B. Now, what about data types in programming languages? So a common data type is the pair. So an example of a pair is if M is a term of type A and N is a term of type B, then an M-N pair is an A cross B pair. And what can I do with a pair? Well, if L is an A times B pair, then I can extract out its first component, first of L, and what will the type of the first component of an A-B pair be? Not everybody all at once. A. And if I also have a pair of type A times B, and I extract out the second component, what will its type be? B. So now if you stare at these bits and these bits, you go, wait, those look kind of similar, right? This has A and B above the line. This has A and B above the line. This is A conjunction B below, and this is A times B below. This is A and B above. This has A below. This has A and B above. This has B below. So a way of interpreting this is to say, what does it mean to have a proof of A and B? Well, it means I've got a pair of things. One is a proof of A, and one is a proof of B. That's just what this says. What does it mean to use a proof of A and B? Well, a proof of this will be a pair of things, a proof of A and a proof of B. So from it, I can extract a proof of A. That's what this does. And I can extract a proof of B. That's what this does. So you can actually identify having a proof of A and B with a pair of proofs. So the pair type and conjunction are identified. So that goes back to the early intuitionists. People like Brouwer and Heiting already had those ideas. But this now goes by the name Curry-Howard because William Howard wrote these out in a very appealing way. But some people, like the Dutch, say, no, it should also be named after BHK, Brouwer, Heiting, and Kolmogorov, or they say it should also be named after De Bruyn, who also did important work in this area. So some people, if you say Curry-Howard correspondence to them, they'll say, oh, you mean the Curry-Howard-De Bruyn correspondence. And so I think I've come to use the name propositions as types instead of Curry-Howard, just to avoid those fights and to acknowledge, right, Curry and Howard did amazing things, but so did Brouwer, Heiting, and Kolmogorov. So anyhow, you've got this idea. When I first saw this, I thought, oh, that's a cute coincidence, right? But it also works for disjunction. It also works for implication. It also works for universal quantifiers. It originally only worked for intuitionistic logic, but then somebody figured out how to make it work for classical logic. Somebody figured out how to make it work for modal logic. There are many different modal logics. One of them corresponds exactly to monads, which is something we use for programming in Haskell all the time. So pretty much every interesting idea in logic has a corresponding interesting idea in computing and vice versa. So that's why propositions as types is so important. And that's why I'm somewhat well known as causing lots of my colleagues to groan because I like to put puns in the titles of things. And this looks like a very dull title, right? Programming Language Foundations in Agda. But it is actually a pun. Can anybody see what the pun is? Any ideas? So the pun is, right? Generally, people would read this as Programming Language Foundations in Agda, the foundations of programming languages. But you can also read it as Programming Language Foundations in Agda because we're doing proofs about language foundations, but what are those proofs? They are programs. So we're also executing everything in Agda. There's a previous book called Software Foundations, also freely available online. A very nice book, except it uses Coq. And I've taught from Coq for 5 years before writing this textbook. My original idea was I would just transliterate the textbook from Coq to Agda, because I thought Agda was a little bit nicer. But then very shortly I went, I don't really like that textbook. So I found myself writing my own textbook. Basically, you should never write a book unless you can not write the book. And soon after I started writing the book and copying the first chapter of Software Foundations, I went, no, I don't want to do this. I want to do it differently. So I found I could not write the book that I ended up writing. That, by the way, is pretty much the only use of classical logic in the book. Yes?
Why did you decide to switch from Coq to Agda in the first place?
Good question. Why did I decide to switch from Coq to Agda? Let me first tell you why it's important. Can I do this? Yeah, I'll go back to that. So to answer your question, right, what's wrong with Coq? So Coq, you can do huge things, right? You can do the proof of the four-color theorem. You can prove an entire C compiler correct. The reason you can do that is you don't write proofs in Coq. You write programs that generate proofs. And so to understand, so this leads to something. First of all, it means you don't just write in one language, you have to write two languages. One, the language in which you describe the language you're compiling, and in which you describe your compiler, and a different language in which you describe the scripts that compute to proofs about these things. So for instance, there, right, I showed you conjunction and pairing are the same thing, but in Coq that gets lost because you deal with conjunction using the scripting language for creating proofs, But pairing is dealt with the language called Galena, which the scripting language manipulates. So you have to learn both the pair type, which is the thing on the bottom, and tactics for manipulating conjunctions, which is the stuff on the top. So everything had to be taught twice. And I found it confusing, and my students found it confusing. Induction in Coq can be mysterious. In the scripting language, you type induct on such and so. Just writing the program doesn't work. You have to execute the program interactively so you can see what your proof state is. So there's no way to just read proofs. What you need to do is execute the proofs. And there are tools that let you execute the proofs, which is great. But it means you can't just sit down and read something. You must execute it interactively. I think being able to execute something interactively is great. But in Agda, you can read the proofs, which I think is better. Induction in particular is very mysterious. You say induct on such and so, and it says, okay, here's your induction hypothesis. And if I'm doing something simple like associativity, I will understand the induction hypothesis. But when I've been doing more complicated things, I've not always understood the induction hypothesis. Fortunately, we've got lots of experts in Coq at the University of Edinburgh. So I go down the hall to Brian McKenna. I said, Brian, why did it do this? Why did Coq do this? And he looks at it, and half the time he says, that's obvious, Phil. It's because da-da-da-da-da. I say, oh, okay, thank you. And half the time he looks at it and he says, I don't know either. Right, so even experts can find which induction hypothesis Coq gives you to be mysterious. So that's not great for teaching students that induction is really easy and straightforward. Whereas in Agda, induction is just recursion, which they already know. This is a more minor point, but in Coq, you define substitution like this, and later they've got something called notations where you can say, oh, but you can write it this way. And that's fine, but then you have two different ways of writing things. And in fact, in software foundations, you could always write things so that you define this once and then forever after use that. And half the time they do things in that idiom, and half the times they define things with a name and then later give a notation for it and use the notation. But it's half with the name and half with the notation. So not so nice. Naming conventions can vary widely. And this idea of propositions as types underlies Coq, but it's very well hidden because of this, because you're doing everything twice. So that's why I was keen to switch to Agda, where pairing and conjunction are identical. There's no difference between them at all. You just do the stuff on the top using the stuff on the bottom. Induction is the same as recursion. It was objecting to me talking about Coq. You can write multi-fixed names with underbars in them so that you don't need special notations. The standard library sort of makes a stab at consistency. And then back to this first point, right, propositions as types underlies everything we do, so that you don't need to teach it separately. In software foundations, there's a separate chapter on propositions as types, which you can skip. Whereas there's nothing separate about propositions as types in my textbook. It's just part of what you do the whole way through. Okay, and then the other thing I want to do is to talk about why do you want a proof assistant? So Bentley Pierce is the guy who began writing software foundations, and then he got many other people to help him with it. And here he explained why he thought using a proof assistant such as Coq is a good idea. And the idea is, right, it's like having one TA per student. The students get immediate feedback if they've done something wrong. And Wednesday and Thursday when I'm teaching, there will be breaks for students to work on their own, and I hope get immediate feedback from Agda that either confirms that they've understood things well or helps them get it right if they've not understood it well. Right? Working with a computer, getting a computer to accept your proof is always very painful. It's much more painful than just writing it out by hand. But I think the pain is worth it because you get immediate feedback. But as you point out, there's one small catch, which is making up the lectures and homeworks. As for the person who teaches the course, not for the person who does the course, it's between 1 and 2 orders of magnitude more work for the instructor, not for the student. So good news, you're the students, I'm the instructor. I did the more work. Although I have to admit that I did not find writing a textbook in Agda significantly harder than writing one just using paper and pencil proofs. And in some ways it was much easier. Right? The book is written in and executes in Agda. All those HTML pages I showed you are typeset by running Agda first. So if I ever make a typo in an Agda program, it will immediately get caught. So that helps me to write a book that's correct. And furthermore, right, you all know how much fun programming is. So on days when I didn't want to write, I could just sit down and say, oh, I'll do this bit of the program. And so in that way, it was actually very helpful. I could be productive even when I didn't want to write, because I could be writing programs that would be the scaffolding for what I would write later. So there's software foundations for you. How are we doing for time? Okay, close to the end. So just a couple of things that I learned from doing the book. The first thing is, what you might say is, yes, but Calc gives you proof scripts, which lets you compact the proofs. The proofs might be a lot smaller if you use Calc proof scripts than if you use Agda. Maybe it's impractical to use Agda. So the answer is, nope, it's not impractical. The programs are about the same size. So progress and preservation are 2 important results in lambda calculus. So progress says, if you have a term, then either, so what we do with terms is we reduce them. So for those of you who know about lambda calculus, this corresponds to beta reduction. So either you can take an evaluation step to the next bit towards being a value, or you're done, which means you have a value. So either you're done computing, or you can take a reduction step. That means you never get stuck. There's never a place where you haven't specified what to do, which is quite important to check. So that's what progress tells you. And then here's the proof of progress. It's this long. I won't go through it in detail. But you can see it has a nice indented form. And in fact, you can read this. I won't read it, but you can go through and read this. And then there's, after I give the code, I explain the code in English. And the structure of the prose here, 3 points, and then this point has 2 subpoints, and the last point has 2 sub-subpoints, exactly matches the structure here. There are 3 points. This first point has 2 subpoints, and then this subpoint has 2 sub-subpoints. So this matches closely. So the code can be read as a guide to the prose, which I find helpful. Here's the same thing done in Software Foundations. The prose proof is very similar. And then here's the proof script. And you can see it's about the same size. But this is actually much harder to read. I think reading any proof that's a proof script in Calc is like reading chess notation without having a chessboard to execute the chess notation on. So something like this cannot be read. It must be executed interactively. So there are trade-offs there, but I like the trade-off of being able to read things. But it's about the same length. You can see this is not significantly shorter. I'm going to skip over that, even though it's interesting. And then the last thing I want to tell you is something interesting I discovered while writing the book. So here's a particular paper out in the literature, and it's talking about getting an evaluator immediately. So an evaluator would say, given a term, what is the value that it evaluates to? So that just means do a reduction step, do a reduction step, do a reduction step. Keep doing it till you get a value out. What they're saying is there's some special purpose ways of doing this. Is when you just do a reduction step, it's called small step semantics. When you evaluate the whole thing, it's called big step semantics. So they're saying we're doing a new version of big step semantics. It's great because you just evaluate stuff. If you do small step semantics, then you can evaluate it, but you need a specialized system, such as this is the K system, and this is the REDX system. So these are two special systems that help you in writing down small step reduction rules and then give you an evaluator based on those small step reduction rules. K is actually working with the firm IOHK that I consult for, and so I knew a lot about K. When I started writing the textbook, I sort of had K envy. I said, I want to just be able to write down the reduction rules and get an evaluator like they do in K. How do I do that? And I pondered it for about 6 months before I realized it's completely obvious. But I'm not the only person who hasn't realized it's completely obvious, right? The authors of this paper clearly didn't think it was completely obvious because they said you can do it with these specialized systems, K and REDX, but not with anything else. In software foundations, they have a specialized tactic for evaluating stuff called normalize. And oh dear, it's a tactic. I don't have those, so I can't even get it that way. But Pierce actually explicitly said, right, lack of animation facilities, by which he meant you have to write a special evaluation tactic. You don't get evaluation for free once you've done the definition. Pierce and many others were involved in something called the POPL Mark Challenge. This was close to a decade ago. One of the challenges is, here's the system, it's called F-sub, prove preservation and progress, the exact results I talked about. And then the next chapter is, so these are tasks to do to show how great your proof assistant is. He did this before he wrote Software Foundations. So he said, right, do a proof of preservation and of progress for this particular type system. And then the next chapter is do an animator. That's something that will, given a term T and T prime, decide whether T evaluates to T. That is, T reduces to T, and it doesn't reduce further. That should mean it's a value. He doesn't even say none of these are what you really want, which is given T, compute T prime and all the reduction steps leading up to it. That's what you'd really like for debugging purposes. Guess what? It's completely obvious that you get this for free. It was actually known for many years to some people. And I asked people, where was this published? And I asked Bob Harper, where was this published? And he said, I really doubt that one can find a citation for 2 + 2 = 4. Bob has a great textbook called Practical Foundations for Programming Languages. But he says of it, I don't discuss animation. It falls under the category of being painfully obvious, right? But lots of us didn't realize it. Bob, of course, is very clever, so he knew. So here's the point. How do you get evaluation? We've already proved it. We've got progress and preservation, and we're working in intuitionistic logic. Very important property of intuitionistic logic. If I tell you A or B is true, I can't just say that. I don't have the law of excluded middle. I can't say A or not A unless I tell you which one. But progress proved inductively tells you which one. Right? So progress, remember, returns either done, meaning it's a value, and it returns a proof it's a value, or it returns step, and it gives you the reduction step. So here, we can just evaluate. To evaluate L, we apply progress to the proof it's well-typed. That either says done and gives you the proof that you're done, or it says step and gives you the next reduction step. But then we have preservation, which tells you that if L is well-typed and it reduces to M, that M is well-typed. So now I know M is well-typed, and I can recursively evaluate on M. Some reduction sequences never terminate. But it's very important in Agda that every program terminate, because every programs might be proofs, and in order to be a valid proof, it must terminate. The program that loops forever can be given any type whatsoever, because when it returns a value of that type. Why is that? Because it never returns. Okay, so a program that loops forever can prove false, which you really don't want to be able to prove. So everything terminates. So how do we make our evaluator terminate? We just give it one more argument, which is a natural number, and we count that down. So the evaluator, in fact, you have to give it a number, it can only do that number of reduction steps. That's fine. It will give you the thing with 100 steps done to it, and you can call it again to do another 100 steps. So you can always evaluate stuff. There's just a little bit that you might have to do by hand. And Connor McBride in particular, right? Some people say, oh, you can only write finite things in strongly typed languages like Agda. No, you can write an evaluator perfectly easily. You just need to do a little bit of work by hand to invoke it or have some framework that lets you do that. So it's completely obvious, of course, that you get an evaluator, but nobody wrote it down before. It is now written down in my textbook. All the examples are computed in exactly this way. Right? Computing precisely an example is actually pretty hard, so I'm glad I can get Agda to evaluate the examples for me. And those of you that take the course, the whole thing you'll be doing on Thursday is learning how to define lambda calculus, and I'll define addition for you, you'll define multiplication, and then you'll get Agda to evaluate the multiplication for you. So the whole goal of the course is I will teach you how you know that 2 plus 2 is 4, and it's your job to work out why 2 times 2 is 4. Oh, there's an actual evaluation of something. They get fairly long-winded, but you can see all the details there, which is great. I'm going to skip over the other thing, which is that we've actually been using this at the cryptocurrency firm I consult for, because we use a variant of lambda calculus on the blockchain, and we can prove things about it correct. If you want to, I'm done. If you want to, sorry for the going over. If you want to know more about propositions as types, there's an article in Communications of the ACM, or if you prefer to watch videos, there's an online video. And I've stopped using Twitter, but a friend who uses Twitter posted this to me. So some people at least seem to like doing the book. Oh yeah, no, this is very important. He mentions he did the proof that multiplication is commutative, and he said, I got way too much serotonin out of it. This is an important thing about using a proof assistant. It's just like playing a video game. When you finally get rid of all the sub-goals and you've completed the proof and Agda says this is done, it just feels like having killed off all the zombies in a video game. So that's great fun. So there's where you can find the textbook. There's the bit that's in GitHub. One great thing I discovered about writing a book in GitHub is when people find typos or other errors in the book, they just submit a pull request and they correct the typo for me. This is so much better than getting an email saying, there's a typo on page such and so, and then I have to go back into LaTeX and correct it. No, they just submit a pull request, and I say accept, and that corrects it. So it's brilliant. We should all be writing our books in GitHub or using some other online technique from now on. It's amazing. I will stop there. Thank you very much.
Okay, thank you very much. And now it's time for questions. So is there anyone that would like to ask something? Okay.
My question is, how much assistance do you get from a proof assistant? So some proofs are...
How much assistance do you get from the proof assistant?
Yeah.
That's a very good question. So the most important assistance that you get is it does the case analysis for you, as I showed.
For associativity, I guess you don't need to prove anything yourself.
So, no. No, for associativity, you do.
Yeah.
And there are two ways of doing it. You can do it equationally, which is what I showed you, or you can do it with rewriting, which is also in the book and which is a bit briefer. There should be better support for doing rewriting with Emacs, but you just sort of have to write out the rewrite statement by hand and then Agda shows you what it's rewritten to. So you can execute things interactively much the way you do in a proof script, but it's a little bit more work by hand, which is less good. So it gives you some assistance. Most important, you can put a hole anywhere in your proof, and it will. That's very good when you're doing. Right, proofs basically work top down. Right, you say, well, I want to prove this. Okay, let's take this one set. Now I've got these two sub-goals to prove, and so on. That's how Coq works. That's how holes in Agda work. So I showed you an example of a hole. So you can write a proof term with a hole in it, and that shows you what you need to fill in the hole. It shows you both the types of all the free variables you have available, so that's what the hypotheses you have to work with, and what conclusion you're trying to prove. So that's the main assistant that Agda gives you, is case analysis and showing you holes and showing you what you have left to do. And that's quite good. That's good enough, but it could be better.
Thank you. Other questions?
Oh, sorry, I forgot the most important proof assistant Agda gives you, which is it gives you a language for writing down the proofs, and then it checks. Right, so the most important thing it gives you is typing Control-C, Control-L, and having things change into color, and having a window at the bottom with no error messages in it. That's the important assistance. Right, and that's what's important for the students.
Other questions?
You mentioned some achievements that were done with Coq, like proving theorems, four-color theorems, and
Yes.
and correctness of a C compiler. Is there something comparable that was done with Agda?
Oh, that's a very good question. So, right, some very large and important proofs have been done with Coq. What's been done with Agda? Much less. Right, so not having proof scripts is a hindrance, I think, for doing large proofs like that. You need some additional support. Agda has a reflection mechanism where you can use Agda to write programs that manipulate Agda proofs that you could use to provide that kind of assistance. But Agda is much less mature than Coq. So there's a large library. Basic libraries of stuff have been done. But in terms of more significant, interesting proofs, no, that's not been done. We need more proof assistance, more support for proof scripting and for proof assistance in Agda before we'll be able to do that. I hope that will come in time, but it's not there yet. That's an important difference between the two.
Yeah.
By the way of this problem, would you conceive a way to transfer automatically proofs from Coq into Agda?
Oh, that's an interesting question. Could you automatically translate Coq to Agda? Yes, you probably could. And in fact, there are quite a few different proof assistants out there by now. There's more than a dozen that people use. So there's a whole workshop on proof interchange. So they look exactly at the question of having a common language that you could translate any of these systems into and then back out of that into any of the other systems. So I'm not very familiar with the work done there, but there certainly will be a lot of work that can be done along those lines. And for that matter, that's what your work is based on doing. So Maria has one idea for how you go about having a common basis for many proof assistants.
Do you see any commercial adoption of Agda in the future, or proof assistance used for commercial applications?
That's a good question. So will there be any commercial adoption of proof assistance? So as I mentioned, I work in cryptocurrencies, things like Bitcoin and Ethereum. And anybody familiar with Ethereum and its smart contracts knows that the main value of those smart contracts so far has been committing fraud. Many people have found ways to break the smart contracts, and they have stolen hundreds of millions of US dollars worth of ether. So there's a high premium on getting things right. Another example for that sort of thing is Intel, many years ago, had a bug in the arithmetic for one of their chips. So they had to do a recall of the chips, which cost hundreds of millions of dollars. So unsurprisingly, people who design chips, like Intel, have become very interested in formal proof and proof assistance. Many, but not all, of the people working in the cryptocurrency space have become interested in formal proof assistance. So there are few proposals for smart currency languages, for smart contract languages. A couple of them already have specifications and proofs of things like type soundness in Coq. This meant that when we did our smart contract for Cardano, which is the cryptocurrency platform for IOHK, which works with a currency called Ada, we had a business case for proving things about it. So I said, we should do an Agda proof of the type theoretical system that we're using to represent proofs on the blockchain. And they said, okay. And they hired the world expert on proving properties of advanced lambda calculi in Agda, a man named James Chapman. And using a chapter of my textbook as the draft, I said, okay, we should do it like this. And then James filled it all in. So we've got a paper submitted for publication on the proof of type soundness of this particular highly theoretical language, but which is also actually used on the blockchain. So basically, find a place where people have lost millions of dollars by getting it wrong, and you'll find people interested in using proof assistance.
Okay. So, other questions? I have myself, and I'd like to ask you, what are the defects of Agda?
What are the defects of Agda? That's a good question. So I think as a programming language, Agda is my absolute favorite. I sometimes describe Agda by saying it's what Haskell wants to be when it grows up. And in fact, Agda was strongly influenced by Haskell. It's a descendant of Haskell. So as a programming language, I don't think it has any defects.
Oh, haha.
However, as a proof system, it certainly does, and this is exactly what we discussed, which is automated assistance for building large proofs is still lacking. So that needs to be developed further in Agda, and it has been developed further in other things like in Coq. So I think Agda will get there eventually, but it's not there yet. That's the important thing. It's missing that it needs.
In fact, Wojciechowski once, who is a famous film analyst, started to think that sooner or later all mathematicians would use proof assistance to formalize the proof. And for what I know, because Coq is much better appealing for mathematicians than Agda. So Agda seems to be more computer science oriented. So that's why you described the defects of Coq, but I wanted to ask you if you see how, that the fact that the tactics are not present in Coq, in Agda, don't help mathematicians to be close to the user to Agda. So I wondered if you have some feedbacks from also the...
So, right, an interesting question is, should mathematicians be using a proof assistant to write their proofs? And the answer, I think, is almost never.
Almost never?
Almost never. Right? It's, right, as discussed, it's 1 to 2 orders of magnitude, 10 to 100 times harder to do a proof with a proof assistant than to do a paper and pencil. So that would make, right, mathematicians already do proofs that are at the limit of what they can do. So I think normally the case for doing a proof with a proof assistant for mathematicians is limited. But there are some places where mathematicians have thought it was important. So one is if the proof is so complicated that you're not sure it's correct. So I think that's exactly why the proof of the 4-color theorem was important, particularly because it was controversial, because a large part of that proof was not paper and pencil, but a computer program written in Fortran. Another place where it's proved to be important is Kepler's conjecture. So there's a man whose name I forget, but you will be able to remind me.
Ailes, Thomas.
Yes.
Tom.
So he has a proof of Kepler's conjecture. He sent it to various journals. And all of them said, we're not sure this is correct, so we're not going to publish this. So he worried for a while and said, what do I do? And then he decided, right, I will use a proof assistant and write out the proof in a proof assistant, and then maybe they will believe it and publish it. So he's got a huge project to do that. He's hired lots of people to help him with the proof. The proof assistant he's using is not Coq, but is Isabelle. And many people, I'm not that familiar with Isabelle, but many people told me that Isabelle gives you proofs that are more readable in the sense that a mathematical proof is readable. So I think that's why Isabelle might have been a good tool for him. So there are a few places where you will want to use a proof assistant, where the proof is so complicated that you're not sure it's right. Another example is the same person, whose name is escaping me, he's French, the same person who did the...
Contier?
Yes. The same person who did the proof of the four-color theorem is now doing a proof of the, I think it's the monster algebra theorem,
Yeah.
right? Something which is published, but it's like 100 pages. So again, you might want some confidence that there are no errors in the proof.
Okay.
So if you need confidence that there are no errors in your proof, then it's worth using a proof assistant. Otherwise, I think I would recommend against it.
Okay, thank you very much. So, thank you very much for your question. Now, thank you. There will be a refreshment in the 7th floor for all. Thank you.